This is VK3 Alpha Mike Lima commencing streaming for this 22nd of September. Sorry, 17th of September 2022. Gosh, I don't know what day it is. I've had a difficult time getting this stream up and running. The camera didn't want to work, then the audio didn't want to work, so it's been a bit of a panic to get it together in time. This week, the subject, the development of the transistor by Bardeen, Brattain and Shockley at Bell Telephone Labs in the late 1940s, and following on from that, the development of the transistor from germanium to silicon, from point contact to junction transistor, and finally the development of the integrated circuit. Who better to describe these inventions but the people who actually invented the device? So tonight, a series of archival films. The originals were in very variable condition. I'll just check that we've got a stream there. Oh dear, the stream page has failed again, so up we come. We go into YouTube Studio. This is a funny sort of an effect we've had the last couple of weeks of the stream disappearing on me. There, let's just see if that comes up. And it looks like it's working. Yep, good. Apologies for the interruption. Okay, back to the subject in hand. The films concerned from the 1940s, 50s and 60s are in many cases beaten about 16mm copies with very bad soundtracks, very faded colour, early colour rendition that I've had to colour shift to get even to an acceptable standard. So without any further ado, let's go straight into the invention of the transistor. And first I'll go on the air. Hello, this is VK3 Alpha Mike Lima with the regular Saturday night test transmission. Tonight, the history of the transistor. From its invention in 1948, and so we'll go straight into that. First of all, the awarding of the Nobel Prize for 1956 to the transistor's three inventors, Bardeen, Brattain and Shockley.
On the 60th anniversary of the death of Alfred Nobel, the prizes bearing his name are awarded at Stockholm, Sweden. The presentations are made by King Gustav Adolf of Sweden in a brilliant setting. Dr. William Shockley is one of three Americans sharing the Physics Award for research which produced the transistor. Dr. John Bardeen shares the prize, which includes a check for $38,700. The third colleague is Dr. Walter Hauser Brattain.
Now, an early documentary on the principles of the transistor made by Mullard in England. This is VK3 Alpha Mike Lima. If you want to find the video that goes with this audio, please Google VK3AML 17 September 2022. That'll bring up the YouTube live stream relating to this. That's VK3AML 17 September 2022. Back to the story of the transistor.
Transistors have much the same function as radio valves, but they have the advantage of being very much smaller and they work with very low voltages. Transistors were invented in 1948, but their origin dates back to the early days of broadcasting when radio receivers looked something like this. This receiver is called a crystal set because it uses a crystal detector. It consists of a coiled, springy silver wire known as the cat's whisker and a crystalline substance such as the natural mineral galena. When the cat's whisker touches certain parts of the crystal, the apparatus allows an electric current to flow more freely in one direction than the other. In other words, it rectifies or detects alternating current. Just how the crystal detector operated was never clearly understood, and with the introduction of the thermionic valve, the crystal detector soon became obsolete. This is an early 5-valve receiver. Since the time that this set was built, valves have been greatly improved and reduced in size so that modern receivers can be made smaller and more efficient. Valves are now used in all manner of electronic equipment, from television receivers containing 20 or more valves to computers like this one at the National Physical Laboratory, which has 5,000 valves. The variety of applications of the valve seemed almost limitless until the development of radar, when certain problems arose which could not be solved by the use of ordinary valves. The radio waves usually used in broadcasting are radiated at a frequency of from 30 kilocycles to 30,000 kilocycles a second. In radar, the frequencies may be 1,000 times higher. At these frequencies, ordinary valves cease to function properly, and in an attempt to solve this problem, crystal detectors in a modified form were once more brought into use, and they worked successfully. This stimulated research into how the crystal operated. Ultimately, this not only resulted in improved crystal rectifiers, or crystal diodes as they are called, but led the way to the transistor. The materials used in crystal diodes and transistors are known as semiconductors. The metal germanium here is a typical semiconductor. To understand its peculiar properties, we must consider why some metals, like copper, conduct electricity well, while other materials do not. To do this, we must study the structure of the atoms of these materials. Every atom consists of a central core, or nucleus, around which revolve a number of smaller particles called electrons. These electrons travel in orbits of different radii. Each electron carries a negative charge of electricity, and the nucleus a positive charge. Only the electrons in the outer orbit play a part in the conduction of electricity. In copper, which is a good conductor of electricity, the electrons of the outer orbits are only loosely bound to their atoms and can move about at random in the spaces between the atoms. When a battery is connected across the two ends of the copper, electrons flow from the negative pole of the battery through the copper and back to the positive pole. The flow is not straight through the copper, but electrons jump from atom to atom. This flow of electrons constitutes an electric current. Now let us consider an insulating material such as porcelain. Here the electrons are tightly bound to their atoms, and they can only be made to move with the greatest difficulty. When we connect up a battery, as we did with the copper, the atoms are under strain, but no current flows, as there are no free electrons to carry it. Now we come to semiconductors. Under normal conditions, the conductivity of these materials is quite low. To see how this comes about, let us have a look at the atomic structure of germanium. The atom of germanium is tetravalent, that is, it has 4 electrons in its outer orbit. Each atom becomes bonded to 4 other atoms, each of the 4 electrons, as it were, bonding with a corresponding electron in a neighboring atom. The bonds in this crystal lattice are very strong and few electrons are free for the conduction of the current. To increase conductivity, the number of free electrons must be increased. One way of doing this is by the application of heat, which causes the crystal lattice to disintegrate. Here is a piece of germanium in series with a battery and lamp. The lamp doesn't light up. Now we heat up the germanium with a flame. And soon the lamp glows brightly. More electrons have been released from the germanium atoms so that more current can flow. When the germanium cools, the current flow falls again. Heating, however, is not a satisfactory method of increasing or controlling conduction, and the problem has been solved in another and more ingenious way by the introduction of other atoms into germanium. Atoms of the metal antimony, for example. Here is the germanium crystal lattice again, and here is an atom of antimony which has 5 electrons in its outer orbit. When introduced into the germanium crystal, 4 of the electrons of this impurity atom bond with 4 adjacent germanium atoms. The 5th electron is then free to leave the atom. Introducing a number of impurity atoms releases sufficient electrons to carry a current when an electric field is applied. The impurity atoms, because they give up electrons, are called donor atoms. A semiconductor like this, in which current is carried by free electrons, is known as N-type. N for negative carrier. Here is a piece of N-type germanium. Notice that it conducts current equally well in either direction without the application of heat. There is another type of impurity which also increases the conduction of pure germanium, the metal indium. Here is the germanium lattice again. The atom of indium, as you see, has only 3 electrons in its outer orbit. When introduced into the germanium crystal, the 3 electrons form bonds with 3 adjacent germanium atoms, leaving a 4th bond incomplete. There will be a space left where we are short of an electron. This space behaves as though there were a localized positive charge ready to capture an electron, and for this reason the region is termed a positive hole. Here are some more impurity atoms giving more positive holes. What we have done, in other words, is to create a shortage of electrons in the germanium. When an electric field is applied, as there are no free electrons available for conduction to take place, some electrons will have to leave their atoms, and when this happens, they leave behind them new positive holes. Some of the electrons will be captured by other positive holes. This process may be continued throughout the germanium, and at the same time that electrons are moving towards the positive pole of the battery, positive holes are moving towards the negative pole. Thus, we can think of the current flow as due entirely to the movement of these positive holes. In fact, we can go further and look upon these holes as positive carriers of electricity, free to move about this material just as electrons move about the N-type material. A semiconductor like this is known as P-type, P for positive carrier. The impurity atoms, because they try to collect electrons, are known as acceptor atoms. Here is a piece of P-type germanium. It looks like ordinary germanium, and current will flow through it in either direction, as with the N-type germanium. Now let us look at a diagram of a piece of P-type and a piece of N-type germanium side by side. Without any battery being connected, The positive carriers in the p-type and negative carriers in the n-type will move about at random. If we stop the movement, we can see that in the p-type germanium on the left will be an equal number of positive carriers and stationary acceptor atoms. Similarly, in the n-type germanium, there will be an equal number of negative carriers and stationary donor atoms. Both pieces of germanium are therefore electrically neutral. Now let us consider what happens when we join the two pieces together. Some of the positive carriers will drift into the n-type germanium. Similarly, some of the negative carriers will drift into the p-type. If we now count up the positive and negative charges, we see that in the p-type there are more negative charges than there are positive charges, so the material has become negatively charged. In the same way, the n-type material has become positively charged. We can represent this state of affairs by an imaginary battery connected like this with a negative pole to the p-type germanium. Because of the electric field existing between the two pieces of germanium, more positive carriers are prevented from entering the positively charged n-type germanium. Like charges repel, remember. And similarly, more negative charges are prevented from entering the negatively charged p-type germanium. Now watch what happens when we connect a real battery like this with the positive pole connected to the p-type and the negative pole to the n-type. The n-type germanium has now become negative with respect to the p-type germanium, and carriers can once more flow. Positive carriers to the n-type and negative carriers to the p-type. Now watch what happens when we reverse the battery. That is, connect the real battery in the same direction as the imaginary battery. Positive carriers will again be repelled from the n-type germanium and negative carriers from the p-type, so that no current flows. If we apply an alternating voltage, current will only flow in one direction. In other words, we can rectify alternating current. Here is a piece of p-type and n-type germanium joined together. You can just see the junction. If now we connect the p-type to the positive pole of the battery and the n-type to the negative pole, the lamp lights. If we reverse the voltage, the lamp does not light. The current only flows in one direction. This is the principle of the germanium diode. Here is one in its small glass protective cover. This matchstick gives you some idea of its size. The diode cannot, of course, amplify. To make this possible, we must add a third component, and when we do this, we have what is called the transistor. This diagram shows a piece of n-type germanium sandwiched between two pieces of p-type germanium. The p-type on the left is known as the emitter, the n-type in the middle, the base, and the p-type on the right, the collector. As before, we can represent the charges on the three components by imaginary batteries. Now a real battery is connected between the base and collector with the negative pole to the collector terminal, the condition for no current flow. A second battery is connected between the base and emitter with the positive pole to the emitter so that current will flow. In this particular type of transistor, it is arranged that there are far fewer electrons in the n-type germanium than there are positive carriers in the p-type, so that for our explanation, we need only consider the flow of positive carriers or holes. Positive holes from the emitter flow into the base. There they will be attracted across the base collector junction into the collector because the collector is negative. With this resistance, we can control the number of positive holes to the base. These in turn determine the current which can flow in the base collector circuit on the right. Not all the positive holes from the emitter flow into the collector. Some of these remain in the base long enough to combine with free electrons there and become neutralized. This gives rise to a small current of electrons flowing into the base to replace those used up in the neutralization process. By varying the flow of electrons into the base, we can, in fact, control the number of holes which reach the collector. It is this control of positive holes which makes it possible for a transistor to amplify. Let us now look at some actual PNP germanium transistors. They are sealed in glass covers like the diodes. This lead goes to the emitter, this one to the base, and this one to the collector. With the cover removed, you can see the construction. There is a central strip of N-type germanium, and on the left, fused into it, is a small blob forming the emitter, and on the right, a larger blob forming the collector. And here is a transistor connected as we saw in the diagram earlier. That's the emitter, the base, and the collector. The emitter is connected through this milliammeter and a resistance, not shown, to the positive pole of a battery. The base is connected through this milliammeter to the negative pole of the battery. The collector is connected through this milliammeter to the negative pole of another battery, and the positive of the battery goes to the base. The emitter current, 4 milliamps in this case, splits up into two parts. The collector current of about 3.8 milliamps and the base current of about 0.2 milliamps. Now watch what happens when we vary the base current. Notice that a small change in the base current produces a large change in the collector current. This is the way we obtain amplification. The transistor can be used instead of an ordinary valve in all kinds of electronic circuits with many advantages. For example, any apparatus employing transistors can be made lighter and more compact. Not only because the transistors themselves are smaller, but because they require such a small power supply. This portable valve radio needs this low-tension battery and this high-tension battery to operate it. In the transistor radio here, this small low-voltage battery is all that is required to operate the receiver for an equivalent time. Another advantage is illustrated in large equipment like this electronic computer. When using valves, 5,000 of them in this case, quite elaborate ventilation systems are required to remove the heat generated by the valves. In transistor-operated equipment, there is practically no heat generated, and the transistors may be mounted close together on panels like this, alongside the other components. One of the earliest applications of transistors was in hearing aid apparatus. This hair grip contains one, complete with amplifier, battery, and microphone. Transistors have developed rapidly, from small ones like this to the larger power-type transistors. Research into new techniques continues, and fresh applications are being discovered all the time.
We are honored now to have with us William Shockley, the inventor of the junction transistor. He was head of the team at Bell Laboratories, which developed the first transistor, and for this, the three men were awarded the Nobel Prize in 1956. Dr. Shockley, I understand you spent your childhood in Palo Alto. How is it your family came here, and from whence did they come?
Well, they came from England. They were both Americans, however. My father was a mining engineer, and I maintain that I am probably a Cockney because I believe in the right weather conditions you could hear the sound of Bow bells from the apartment where I was born. But I arrived in Palo Alto when I was 3 years old, went to school here, including the Palo Alto Military Academy, which is still going, and then did my high school in Hollywood High School in Los Angeles.
And then you went on to college?
Yes, I went to Caltech for my undergraduate work and then to MIT for a PhD. I was a physics major from about my sophomore year in college.
And after your PhD, armed with your diploma, where did you go?
I went to Bell Telephone Laboratories at that time, where I worked for C.J. Davison, who won the Nobel Prize around 1938 for electron diffraction. And he was one of the attractions that brought me to Bell Laboratories.
Little did he think he had another Nobel Prize winner coming to work for him, I'm sure. What were you looking for, or what were you working on when you joined Bell Lab? What was your your subject of research?
If I were asked to plan a better procedure than Bell Labs used to try to get me into the transistor business, it would be actually hard to do. They took me away from Davison temporarily to begin with and had me work in the vacuum tube laboratory. And I was given a lecture by the then research director, Dr. Kelly, saying that he looked forward to the time when we would get all of the relays that make contacts in the telephone exchange out of the telephone exchange and replace them with something electronic so they'd have less trouble. And I wanted to get back to solid-state physics, which was the field in which I had got my PhD, and I tried to see how to put these two things together, how to do something electronic and make amplifiers, but to do it not with vacuum, not with a vacuum of vacuum tubes, but to try to find out some way to do this with solid materials.
So you were looking for an amplifier?
Yes, my first notebook entries, which are very important in a laboratory. When you think you've invented something, you write it down in your notebook and get someone to witness it. My first notebook entry on what might have been a working transistor was, as I recall, late 1939.
And how many years was it before you really felt you had something to present?
Well, the war intervened, and during that time I went out of physics and worked on problems of military operations, what is now called operations research. As a matter of fact, the name was invented then. And after that, I came back. There was reorganization in Bell Laboratories, and I picked the objective of trying to see if we could make something which would do the same sort of job as a vacuum tube, but to do it with crystal detectors. The same sort of materials that have been used in the war to do the detection that goes along with the klystrons that we heard about earlier today.
This seems like a reverting back to almost aboriginal electronics. We're taking the crystal detector. Tell me how you happen to go from there to your transistor. Could this have been an accidental discovery?
Well, it could have been an accidental discovery, I believe. It didn't come that way. As a matter of fact, all of the theory that we needed to do transistors had been well developed before we really got one to work, and even after the point contact first worked, it was still some time before we saw the really simpler matter of the junction transistor. But it could have been an accident, I believe, because during the war, and in fact back to the 1910s, it was found that if you made a cat's whisker detector, which consists of putting a point contact on a crystal, let this book represent the crystal, this has rectifying electrical properties. Now, if someone had simply studied the interaction of two points electrically on one another as they were brought close together, it's quite possible that a transistor might have been invented back in 1915.
Could we have skipped the whole vacuum tube technology then?
Well, I would be very reluctant to take a position on that because of the extremely competitive attitude between the vacuum and the solid-state electronics. I think they have been supplementary, and there are many things that can be done with vacuum tubes that the transistor can't do today, and this may remain. Of course, there's competition. People are hoping that somehow, by solid-state means, one will be able to make a flat television tube, for example, which now requires a long shot of an electron beam.
Looking forward to the new inventions that are yet to come, I'd like to have you tell me your thoughts on the nurturing of creativity in the young people today, in our homes and in our schools. I know you've done some deep thinking on this. I'd like to know your thoughts on it.
Well, I think a good deal of it is probably built in genetically when the individual starts out, but it can certainly be discouraged. I think one of the things that is least effective in encouraging creativity is to give the impression that the student so often gets in school that all of the nice things, the important things, are found out nicely and neatly. It has been my experience that everything, all of the more difficult inventions I've made, and I counted recently and I find I have some 85 issued patents, which makes me at least close to being in the major league on numbers. Most of these require many failures to accomplish. One must, it's my own experience that to do creative work, one must overextend oneself, one must count on falling on his face, on getting into difficulties. One must learn from these failures and not be stopped by them. But if one is taught that everything is neat and orderly and one never gets into a mess when trying to do anything new, then he will be so conservative that I don't think he'll break new ground. I think the big contribution that can be made, maybe the biggest educational contribution that could be made to the creativity of people, is to persuade them that they shouldn't worry about making mistakes. This will be inevitable if they are going to really do anything new.
Thank you very much, Dr. Shockley.
And this is VK3AML.
Ever assembled. The year, 1947. And this is one of the latest transistors, a much more sophisticated device, but based on the same physical principles as its ancestor. The impact of the transistor on the electronic industry and on our society is unquestioned. What is the origin of this remarkable device? The discovery of the transistor is the result of scientific research. Research by men of insight who sought to understand the atomic structure and electrical behavior of semiconductors which had intrigued them for years. For example, electrical conductivity of semiconductors like germanium lies somewhere between that of good conductors like copper and good insulators like rubber. Conductivity of semiconductors increases when their temperature is raised. Conductivity of metals decreases when they are heated. Conductivity of most semiconductors, like germanium, increases when they are exposed to light. And when a metal, like this copper wire, is in contact with a semiconductor, in this case a piece of germanium, conductivity is less in one direction than the other. This characteristic of semiconductors was exploited in the early days of radio to make excellent radio detectors using lead sulfide or silicon. When these semiconductors were touched with a fine wire called a cat's whisker, they changed the incoming high-frequency signal to a low-frequency signal, which could then be heard with earphones. Later, semiconductors were used to build devices like this copper oxide rectifier for telephone systems. And cat's whisker rectifiers were reactivated during World War II for microwave radar. Even though semiconductors were being used, they were not fully understood. Thus, after the war, Bell Telephone Laboratories intensified the investigation of semiconductors with a hope for understanding. Understanding might bring control, and control was the key to further use. Bell Laboratories scientists decided to study silicon and germanium, which are the simplest semiconductors. The work proceeded in two areas: the studies of bulk properties and surface properties. At a very early stage of the investigation, William Shockley predicted from existing theories of electrical conduction in semiconductors that it should be possible to control the supply of electrons near the surface of a semiconductor by influencing them with an electric field imposed from the outside. If true, this might lead to a new amplifier without the limitations of the electron tube. Shockley devised some experiments to test his hypothesis, but was unable to secure satisfactory results. The negative result of the field effect experiments was an important factor in suggesting to John Bardeen that electrons were trapped in the surface of the semiconductor. This theory suggested new experiments which Walter Brattain carried out. Recently, Dr. Brattain described some of the experiments.
One of the types of measurements that was being done was to measure the contact potential of the surface of germanium. One did this after the fashion of the first experiment on contact potential by Kelvin, by having a semiconductor surface with electrical contact to the semiconductor and placing close to the semiconductor a metal conductor. If one moved the metal conductor with respect to the semiconductor, one in general got current flow in the external circuit. But one found, as Kelvin did, that if one put in a battery of the proper amount, one could move the metal with respect to the semiconductor without getting any current. In studying this effect, we decided at one time to see if we could do this when the whole system was immersed in a liquid. The phenomena that resulted were very interesting, and we finally decided that by using an electrolyte, one should be able to make, in principle, an amplifier out of a semiconductor. One morning, after we had discussed the results of this type of experiment, John Bardeen walked into my office and suggested a geometry for producing an amplifier using the electrolyte.
Bardeen suggested that on a piece of germanium they place a drop of electrolyte, in this case, water. Then to wax a metal wire and push it through the water to make contact with the germanium. The wax would insulate the wire from the water. Another point would make contact with the water. Potentials would be supplied between the water and the germanium, and also between the wax point and the germanium. It was thought that the potential on the electrolyte would influence the flow of current between the wax point and the germanium. This experiment worked. They had produced a semiconductor amplifier. This experiment was the key that led to the invention of the transistor. But there were several problems. The water evaporated too quickly. So they changed the electrolyte to glycoborate, which evaporates very slowly. This worked quite well. But the device would not amplify above 8 cycles per second. They were quite sure that the electrolyte was responsible for the slow response. They tried to replace the electrolyte and its contact with a spot of gold. Instead of the waxed point, they placed a wire contact near the edge of the gold spot. It was then they observed an entirely new phenomenon, now called the transistor effect. 4 days later, on December 23, 1947, utilizing the transistor effect, the very first transistor was made. This was an eventful day, and Walter Brattain recorded the events.
My notes for the day say this. Using the germanium surface, see top of page 197, and the gold contacts, the following circuit was set up. This circuit was actually spoken over, and by switching the device in and out, a distinct gain in speech level could be heard and seen on the scope presentation with no noticeable change in quality. By measurements at a fixed frequency, it was determined that the power gain was of the order of a factor of 18 or greater. Various people were present and witnessed this test and listened, of whom some were the following: R.B. Gibney, H.R. Moore, J. Bardeen, G.L. Pearson, W. Shockley, H. Fletcher, and R. Bowen. Mr. H.R. Moore assisted in setting up the circuit, and the demonstration occurred on the afternoon of December 23, 1947.
The question in everyone's mind at the time was, could this embryo amplifier be the hoped-for prize, or was it merely an erratic laboratory curiosity? Could it be made into a thoroughly practical device? This challenge was taken up by the Design and Development Group. This new device had to meet extended performance requirements, be reliable, and yet be economically feasible to produce. The point contact transistor was the first production line model. Further understanding and control led to the growing of single crystals of germanium and made possible William Shockley's concept of a junction transistor. This was in 1951. A few years later, the alloy transistor was developed. The industry was now in a period of substantial growth, but more work lay ahead. The frequency of the alloy transistor was definitely limited, and it could only be produced on a one-at-a-time basis. Now came another breakthrough: the diffused base transistor, which is a high-frequency, high-speed device. Working together, the development and manufacturing groups developed today's production methods. Now, a single slice of silicon may contain as many as 2,000 transistors. The transistor is a truly remarkable device. One of its features is its ability to perform at very low power levels. As demonstrated here, the light energy from a burning match falling on a solar battery is sufficient to drive this transistor oscillator. A more important feature of the transistor is its reliability, its ability to operate for extended periods of time without changing. It can also transmit and amplify high-frequency signals at very high speed. All these features contribute to modern switching in computer systems. This tiny electronic device is the outcome of scientific research by trained men dedicated to understanding, working in an environment which fosters the uninhibited search for answers to riddles of science which are related to communications needs. For their discovery of the transistor effect, John Bardeen, Walter Brattain, and William Shockley in 1956 shared the highest honor in science, the Nobel Prize.
And no, it's not the end. This is VK3 Alpha Mike Lima with the regular Saturday night test transmission. This week, the invention of the transistor and the integrated circuit. And for this reason, we're showing a series of films shot at the time of the invention of both and featuring interviews with people who were involved with the invention of the transistor and the IC. So you're getting it from the horse's mouth. This is VK3 Alpha Mike Lima. No, I'm not a horse, but let's get you back to the documentaries. And those who are listening on 2 meters, if you want to look at the video associated with these soundtracks, these documentaries, please Google VK3AML 17 September 2022. That's VK3AML 17 September 2022, and that phrase should get you to our live stream on YouTube. Back to the documentary.
Western Electric, 30 years ago, before solid-state electronics and transistors. From factories like this came a nationwide switching network connecting millions of telephones. If only 2 phones existed, only 2 wires would be needed to connect them. 10 phones would require 90 wires to reach each other, if no switching means were available. The 85 million phones in actual use today would need an astronomical number of wires without an adequate switching system. The switching network built by Western Electric includes over 10,000 major switching centers that enable any phone to reach any other phone using the minimum number of channels. The network has served and grown without interruption for nearly a century. New products and techniques have kept it up to date, always working. Today, the electronics revolution has transformed manufacturing. New kinds of challenges confront communications scientists and engineers. To make today's components, they must probe matter more deeply. To solve problems of material characteristics, to deal with temperatures from 200 degrees below to 2,000 degrees above zero Fahrenheit. They must create new materials and shape them on a molecular scale. This requires new tools, new processing techniques, an entirely new manufacturing environment. Precision is essential at every step in processing and measurement. Microscopes and instruments extend the capabilities of eyes and fingers, increasing skills. Atmosphere must be controlled, from tremendous pressures to a high vacuum previously found only in space. And dirt and dust must be excluded. Sometimes light and color must be controlled. From this new environment is now emerging the hardware of an important development in communications. Number one, ESS, an electronic switching system. Designed by Bell Telephone Laboratories, ESS is manufactured by Western Electric for the Bell system to meet the challenge of expanding telephone needs. ESS represents a radical advance in making telephone connections. Virtually all electronic, it uses magnetically stored information to control the operations necessary to put through a call. An incoming call is detected by scanners, which report it to central control. Central control routes the number being called into a temporary memory unit, where it is held. Then, using the semi-permanent memory unit, central control determines whether the call is local or long distance, and what lines must be used to make connections. This information is contained in magnetized memory cards that function somewhat like punched cards used with business machines. The cards can be easily removed for alteration of the information. When central control has obtained all the data necessary for completing the call, it issues instructions to the switching network. The network, together with circuits that lead to trunk and local lines, performs the physical functions that connect the telephones. The time from the moment dialing is completed to the moment the called number rings is a small fraction of a second. ESS offers uniquely flexible, convenient service. It can transfer your calls to another phone when you're away from your own. If you're busy talking, it can automatically signal you that another call is trying to reach you. It can set up conference calls. And dialing just a few digits will connect you to numbers you call frequently. The key to these services is stored program control. Part of this control system is the semi-permanent memory unit, called the Transistor module. In its manufacture and assembly, new processes and tools are being developed to assist human skills in achieving greater precision and uniformity. Access to information stored on the memory cards is provided by special twister wire. To make this wire, a thin permalloy tape is wrapped in a spiral around a small copper wire, thinner than hair, at 12,000 revolutions per minute. The tape itself is formed from wire under a pressure of 1 million pounds per square inch. Any dirt or imperfection in the metal, even a 10,000th of an inch in size, can ruin a complete memory unit. "45 twister wires, along with accompanying conductor wires, are embedded by heat between two mylar polyethylene belts. Wire placement is checked in the finished cable. During the early years of manufacture, electrical test records were kept on every thousandth of an inch of twister wire, allowing a check on later performance. Here, as in most ESS manufacture, quality depends on precision. When the twister module is assembled, twister wires line up at right angles to copper straps, which function as solenoids. There are more than 300,000 intersections in each memory module. Not one wire can vary in position more than 3/1000ths of an inch. A typical ESS program store includes 16 wired modules with a capacity of nearly 6 million information bits. More than half are used for self-checking maintenance programs. The rest used for more versatile switching programs than is possible with the electromechanical system still in general use. Another high production component, the sealed contact. This is the basic element of the ferried switch that performs line switching functions in ESS. Millions of such contacts will be needed every year. From preparation of the iron-nickel reeds to final assembly, mechanized processes are brought into play. There have been many production problems to solve. Not even a speck of dust 1/1000th of an inch in size can be tolerated. Also, the reeds are soft after annealing. Human handling had to be avoided. The solution? Loading and transporting the reeds in racks through gold and silver plating to chemical and ultrasonic cleaning. A pair of reeds are sealed under pressure in a small glass capsule. Production problems must be solved every day. For example, unstable contact resistance. Its causes were not fully understood, especially in the early stage of manufacture. But the facts leading to a solution are coming from constant research and testing. The ferried switch, which uses sealed contacts, represents a great advance in switching. When performance and economy become competitive, further advances will probably come from solid-state technology. Here is a world where material is grown into crystals with controlled impurities, with intolerances which are molecular, even atomic. The objective? Semiconductors, transistors, and diodes needed by the millions for ESS offices. Bell Laboratories' invention of the transistor and its later work in semiconductors made the basic concept of electronic switching a practicality. This single silicon crystal will be trimmed, then sliced and diced. These slices have been cleaned in a liquid by means of ultrasonic energy. A special technique, called epitaxial deposition, involves the growing of molecular layers in an oven to extend the originally grown crystal structure of the silicon slices. Control of temperature is critical. It must be uniform across the slices. Materials such as boron and phosphorus are diffused into the silicon to provide desired electronic characteristics. This diffusion is measured in parts per billion. Patterns are made by a photographic process and then micro-machined by chemical etching to produce nearly 1,700 transistors on each slice. Testing and measuring are continuous for resistivity, for thickness. These are controlled to rigid specifications to suit many applications. Hundreds of solid-state components nearly ready for cutting. New processing techniques are increasing semiconductor production rates as well as improving quality and reducing unit cost.
And here you see why early transistors were so expensive. They were made one by one. This is VK3 Alpha Mike Lima, by the way.
As solid-state manufacture becomes increasingly sub-miniaturized, problems multiply. For example, in attaching leads. Gold wire, 1/1000th of an inch thick, is joined to thin aluminum electrodes that have a bonding area only a few thousandths of an inch square. Connections are made at a rate of 400 transistors per hour. Semiconductors must meet reliability and performance requirements matched only in missile and space technology. To assure uninterrupted service, major ESS units are duplicated in each installation. Alternate routing is accomplished in microseconds. There is a continuing challenge. Increase the production rate of ESS units to reduce costs and at the same time improve unit quality. The challenge can be met by improving design and manufacturing techniques.
Like surface
In the
mount.
case of the ferried switch assembly, a newly developed concept makes it possible to wind 64 coils in one continuous operation. Mechanized processes such as this are expected to increase ESS frame production at a very rapid rate within the next decade. There are many specific manufacturing challenges. Operations such as wiring the ferrite memory module depend on human skills supplemented by training and expert supervision.
The days of magnetic memory, long gone.
Manufacturing a complex system is accomplished by dividing the process into many separate operations, such as this. Intricate yet compact circuits allow ESS to check itself continuously, report a change in component performance that may lead to failure, and direct replacement of the suspected unit. Faster switching and continual self-maintenance enable an ESS office to process many more calls than previous electromechanical systems, while requiring less space. Somewhat like a teaching machine, a wiring assist device uses punched tape, which causes a sequence of lights to direct the operator's work. In all areas of ESS manufacture, solving production problems has required a new look at the skills of people and machines, a search for the best ways to combine them. Human sensing, judging, and tactile abilities often provide a more suitable solution to a production problem than can be offered by the most complex machinery. ESS units are designed for a minimum of interconnections at the final installation, so that most of the wiring and much of the detailed testing can be done at the factory. Thus, manufacturing responsibility extends far beyond the making of parts to include integrated construction of an entire system. This manufacturing experience has already led to even more sophisticated processes and devices that may find application in future systems. One of the most promising developments, thin film circuits. In a unique moving line vacuum chamber, pure metal is deposited on glass or ceramic plates in a film only 4/millionths of an inch thick. Using an emulsion sensitive to ultraviolet light, photoresist processes generate circuit patterns. The negative design permits certain areas of the plate to be exposed. The pattern is varied according to the desired circuit application. The exposed area is etched off. Greatly magnified on a shadow graph, a resistor pattern is checked for precision. Each plate contains 54 complete resistors and interconnections. These thin film resistors can be adjusted to close tolerances. They're extremely stable and economical to manufacture. Contact areas for leads are deposited by a sputtering process. The basic goal, whatever the product, make it smaller, more reliable, more economical, extend its function. Beam lead and multiple chip circuits are a step toward fully integrated circuits grown into a single block of semiconductor materials. This is the threshold of electronic telephone switching. In the years ahead, electronic central offices will bring new and better kinds of service to the telephone user.
And that was a Bell Telephone Labs documentary from 1968. And this is VK3 Alpha Mike Lima. VK3AML. If anybody cares to look in on the video of this, please Google VK3AML 17 September 2022. That's VK3AML 17 September 2022. Now, on the invention of the integrated circuit.
PN junctions from a pile of sand. Planar silicon integrated circuits. Invented here. The epitaxial process, a secret locked in a crystal, higher yields in 1/10 the time. Invented here. Metal over oxide. You can't make an integrated circuit without it. Invented here.
By Fairchild, which is now no longer existing.
Fairchild brought out the first NPN silicon mesa double diffuse transistor. The first PNP silicon mesa double diffuse transistor, the first lifetime controlled silicon planar transistor, the first planar epitaxial PNP transistor, the first silicon RF transistor, the first planar 2 transistor, the first planar silicon controlled rectifier, the first planar epitaxial power transistor, the first resistor transistor logic family, the first complementary transistor logic family, the first dual inline package, the first commercially available face-down bonded circuit. Processes, product, packages, price. Oh yes, and production. Invented here.
Let's get started, Jim, by you saying what is an integrated circuit.
Here is a packaged integrated circuit. Inside this package is a chip of silicon which provides the electrical equivalent of many transistors, resistors, and diodes, all interconnected to provide the desired function. Before we discuss in detail what's inside that package, I'd like to show you some evolutionary examples of what integrated circuits can do for the appearance of electronic equipment. Here is a photograph of a printed circuit board from a digital computer a la 1960.
Prehistoric.
Right, built out of transistors, separate resistors, and diodes, wired together on the printed circuit board. Here is the electrical equivalent of the circuit you saw in the previous photograph, built in integrated circuit form of vintage 1963. Notice how much smaller and simpler this board is. I have here a newer version of integrated circuits containing in the upper left-hand corner 8 integrated circuits outlined. Now those 8 integrated circuits provide essentially the same function that was provided by this board, namely 24 integrated circuits down to 8. Notice that the wiring on this package is extremely orderly and well organized.
I see less pin connections, too.
This is perhaps typical, Harry, that we find as we make a more complex function in one structure, the number of pins tends to go up only as roughly the square root of the complexity that's provided by that board. Now you've seen an evolution of transistors to early integrated circuits,
to modern ones, let me show you a series of photographs which shows you what's inside the corresponding cans. Here is a photograph of a single transistor chip, such as we might find in the 1960 version of the computer board I showed you.
Old style again.
Here's the intermediate style. You remember the 1963 integrated circuit packages. Here's what would be in one of them, typically 10 transistors. Here is a modern 1966 version of integrated circuits with many hundreds of components on this one circuit. This particular function provides 16 bits of digital memory in this one package. Now, integrated circuits can not only be used for digital, but also for linear service. Here is an IF strip, transistorized and hence perhaps 3 years old. Here is its integrated circuit counterpart, providing exactly the same function. Notice how much simpler it is. The wiring is roughly the same. The simplicity is greater. Hence, we can expect that it will not only be cheaper, but more reliable. And these are perhaps the most important contributions of integrated circuits.
Let's get on to how to design an integrated circuit.
All right? Let's do it by way of an example. Up here we have a circuit or a typical structure which might be in integrated form. This particular circuit has 20 components in it: diodes, transistors, and resistors. After the configuration has been chosen by usual techniques, the next step is to build a breadboard model in actual working form. On the breadboard, we have separate transistors and other components, all actually wired into a working circuit. The purpose of working with the breadboard is to try to optimize the numerical value of each of the components in the circuit. Once this optimization has been achieved, the next job is the design of the masks, which will be used to make the integrated circuit. Harry, I wonder if you could cover some of that work.
Yes, I can. So, we made the engineer pick up a soldering iron. Let's see if we can make an artist out of him by using yet another example. Here is a full-scale 30 by 30 inch piece of typical integrated circuit artwork, which represents in a careful, precise form the interconnection pattern of an integrated circuit. For example, these are the metal pads. These will be on the integrated circuit, the metal pads which connect to the outside world. Here we have the transistors. And here are diodes and more interconnecting metals. The problem here is to very carefully and precisely convert this large-scale drawing into a small, precise version of this on a 2 by 2 inch glass plate. This artwork is reduced 500 times by a process of high-resolution photography to a glass plate upon which the pattern shown by the artwork is successively stepped and exposed all the way across the glass up to 1,500 times, which means, of course, 1,500 integrated circuits. Now, the artwork which I showed was only one mask, potentially. Here is the artwork in reduced plastic overlay version, which goes with a complete set to make an integrated circuit. There are 5 to 7 or even more of these potential masks. All of these must align carefully and precisely. These then will be translated into another set of glass masks, which will then be used for contact printing directly onto silicon wafers. In working with silicon, this is what you begin with, a silicon ingot. It's a glass-like material, very brittle, very much like diamond. In fact, it costs about like diamond and is a member of the diamond family. This is made in a series of long rods by a process known as crystal pulling. It cools as it is pulled. However, it is still very hot since it's been grown at a very high temperature, up around the region of 1,400 degrees centigrade. We cut this into thin wafers, about 12 thousandths of an inch thick, by using a diamond saw. After cutting, the wafers are very carefully polished, so you end up with a mirror-like surface, which is essential in the preparation of the integrated circuits. The finished chip is about 5 thousandths of an inch thick. Let's take a look inside the silicon. This is a cross-section of the wafer we've just watched being made. To protect it from the outside world, we allow oxygen to react with the top surface and grow an oxide called the passivating silicon dioxide layer. Now we're going to make use of the masks we made earlier. First, the wafer is coated with a photosensitive resin. The mask is then placed on the wafer, and the system is then exposed to light. As a result, the exposed resin hardens. The remaining resin can be simply rinsed away. The wafer is then exposed to acid. Those areas of the passivating layer not protected by the hardened resin are etched away. In the next operation, called diffusion, the wafer is exposed to a dopant. This impurity diffuses through the window and into the silicon below, forming the collector of a transistor in our integrated circuit. But notice, at the same time diffusion is taking place, more oxide is being formed. This is the essence of the planar process. Now we're going to strip off the passivating layer and grow a new layer of silicon right on top of the diffused wafer by a process called epitaxial growth. Now we form electrically isolated regions on the wafer by a process of diffusion. Photosensitive coating, masking, exposure, rinsing, etching, and diffusion. Next, we prepare the individual parts of the integrated circuit. First, a transistor base and a resistor. The same procedure is followed. Notice that diffusion takes place not only downwards, but also laterally under the oxide. As a result, the junction is formed beneath the passivating layer, where it is protected from the outside world. The next diffusion forms an emitter and a collector contact to complete the transistor. Again, the same process. The next step enables us to interconnect the various components and to make contact with them. Again, we'll etch windows in the oxide. But instead of another diffusion, a layer of metal is deposited over the entire surface of the wafer. Then, by use of the proper masks, the excess metal can be etched away. Sometimes we like to make resistors a different way, by using the metal interconnection pattern. All you have to do is make the metal pathway a little narrower, and it provides higher resistance. If we wish to make a capacitor, we take advantage of the fact that the oxide layer is an excellent dielectric material. A small area of metal is deposited, forming one plate of a capacitor. The oxide is the dielectric, and the silicon directly below the oxide forms the other plate. The series of schematic operations taking place on one structure that you just saw actually takes place across a whole wafer. This results in a wafer containing many integrated circuits, up to 1,500 of them. Now comes the electrical testing of this wafer. Jim, can you take over on this part?
Certainly, Harry. Even though we have been very careful in fabricating this wafer containing many hundreds of integrated circuits, not all the circuits on the wafer are flawless. The first job is to determine and mark those circuits which are not good. We test the wafer in a probe testing machine. We then scribe the wafer using a diamond point in a scribing machine. After separating, cleaning, and drying the integrated circuits, we fish out the ones that are bad. If we have been successful to this point, we have a high yield of good ones. From this point on, we are going to package the circuits, and so whenever we throw one away, we're going to throw away a complete package.
That's a good point, Jim. Let's look into this matter of packaging a little bit. You know, we've exercised a lot of care in bringing the integrated circuit chip to this point in the processing, and we've also done it economically, because mostly we've processed them as wafers, 1,500 at a time. From here on out, as you pointed out, we will be handling them as individuals, putting expensive packages around them. So how we treat the packages is important. In the old days, it was simple. You had a wide choice, two, large and small. A TO18 outline, small, and the TO5 larger outline. These days, we have upwards of 250 varieties of packages, and a user can select any one of them. Here are an example of three of these. A dual inline package, a plastic package, and a flat pack. The most nearly universal of these is the dual inline package. Let's take a closer look at just how that is made. You start out with the idea that you're going to build a tasty but inedible sandwich. Here are the two halves that you begin with. Two ceramic parts into which the integrated circuit chip will form the sandwich meat.
And we'll be going live at about 10 minutes past 11 Melbourne time. This is VK3AML, and we're currently watching a documentary made about the year 1970 by Fairchild Electronics, which ceased to exist in about 1983, I think, about their development of the integrated circuit. You'll see circular package 741s in this, as well as the dual inline packages that are more familiar today. Back to the Fairchild documentary until 10 past 11.
The two halves are glassed with a material which will form the solder that glues the two halves together later. A Kovar frame has been prepared in advance and cut out to the pattern necessary to connect the chip to the outside world. This Kovar frame will also be placed in the middle of the sandwich alongside of the chip. And here is the arrangement. Chip in center, Kovar frame around the outside, and notice that the tips of the frame here have been metallized. This will form the connection to the chip directly. As shown here, where the lead bond wires have been placed connecting the pads on the chip to the metallized tips of the Kovar frame. We complete the sandwich by putting the top half of the package right on top of the frame. The next operation will be to clip the ends of the frame. The package is now revealed in its magnificent beauty. The solder glass is peeping out, so that we have to clean that up a little bit by sending the part through the furnace along with many thousands of others, so that the solder glass is all melted in and neatly arranged in place. This is the finished dual inline package.
Now that the circuit has been packaged, we must again test it substantially before we would dare ship it to the user. First is a series of electrical tests, many of which use special test equipment, which is again built from integrated circuits. Many of the tests made on the integrated circuits now duplicate those tests which were made on the wafers. In addition to these tests, which duplicate those which were made before, we must make some special tests, such as frequency response of a linear amplifier or switching speed of a digital circuit, before we would dare ship the unit. We can't make these tests on the wafer state due to the limitations of the test equipment through the probes. In addition to these electrical tests, we make a variety of mechanical tests, such as shock, vibration, and acceleration. Finally, we make a set of temperature tests, running the unit at high temperature and at low temperature to ensure that the unit will work dependably in service.
Now let's look into some of the things that we can do with integrated circuits. But first, a commercial.
For the past year or so, Fairchild has been publishing a series of applications notes on integrated...
And I'm letting this slip through because Fairchild no longer exists, so this is not a valid advert.
They talk about the switch to integrated circuits, how to design them in, when to use them, which ones, their costs, basic design rules. A pretty complete short course. Then, on the back of each sheet, we've covered a specific industrial application, an XY controller, a tape reader and display, a cycloconverter. A dozen ideas. But if you're really serious, you'll have to read the book. It covers all the IC families. Digital, linear, hybrid, memory, custom. It tells about packaging, testing, and of course, how to order ICs. Altogether, that's about 100 pages of fresh information on integrated circuits. We'll send it to you if you'll write us. Got a pencil? Fairchild TV Briefing.
No, we won't include that. That address, I think, ceased to exist in about 1970. This is a documentary on the integrated circuit and its invention by Fairchild, filmed about 50 years ago.
Design, build, and test integrated circuits. Let's look at some of the functions which are available now in integrated circuit form. Here is a list of readily available digital circuit functions. This list includes about all the circuits which are needed to build the electronics part of a digital computer. This list of linear functions includes a large variety of things. As you probably know, operational amplifiers, for example, are rather precise amplifiers that are used as the major building block of analog computers. The voltage comparator is a circuit which very accurately compares which of two voltages is the larger.
You know, it's exciting to think that all of these functions are here today. They can be used, they're available. And it's even more exciting when you consider the number of applications that these can be put to. You couldn't even begin to make a list of all of them. Actually, the uses of integrated circuits are limited only by those who are designing these uses. Let's take a deeper look into some of the present-day applications of integrated circuits.
One of the many industrial companies using integrated circuits today is Burroughs Corporation. At Burroughs, integrated circuits in dual inline packages are inserted in circuit boards automatically, affording more efficient production. Using this machine, which is proprietary with Burroughs, a single integrated circuit can be installed for about the same cost it previously took to install a discrete component. In order to automate the entire manufacturing process, Burroughs uses other advanced techniques such as flow soldering. This guarantees reliable connections to each integrated circuit. In addition, computerized wire wrapping machines are used to make the backplane interconnections so that the inherent reliability of the integrated design isn't compromised. The machine automatically cuts each wire to the correct length, strips the ends, routes the wires, and makes the connections. Meanwhile, each completed circuit board is tested individually. Finally, circuit boards are installed in the computer frame and the completed system is thoroughly tested. Burroughs is now committed to integrated circuits and, in fact, recently placed one of the largest single orders ever placed for these devices. For Burroughs, integrated circuits provide a significant cost reduction and a proven increase in reliability, both of which are real benefits to Burroughs customers. Stromberg Carlson is another company committed to integrated circuits. Their data products division is now manufacturing the first in a line of new Stromberg Carlson products built with ICs. Integrated circuits, in this case in TO5 packages, both metal and plastic, were used in the SC1100 because of their low cost, size, reliability, and, as Stromberg Carlson says, because integrated circuits are here to stay. The SC1100 system consists of up to 18 desktop interrogators like this one, which are handled by a single station control unit, which in turn ties into the computer memory. The operator asks the computer a coded question on the interrogator. The computer responds with the requested information almost instantly. For instance, with an employee personnel record. This is the Model 388 AM/FM stereo receiver built by H.8 Scott. It's only one of a new line of hi-fi components in which linear integrated circuits replace discrete transistors.
Live callback in 6 minutes, VK3AML.
Scott engineers have chosen ICs for one specific purpose: better performance. More stations can be pulled in with less noise and interference. Weak stations become loud and clear, and outside interference is drastically reduced. But there are other benefits too. A total of 37 discrete components in the receiver's IF strip have been replaced by only 4 ICs. This new approach to circuit design promises even more dramatic new products from the people at H.H. Scott. We've seen some examples of how industry is putting integrated circuits to work today. But how about the future?
Well, that's a very exciting part of the story. Research is constantly going on to find new ways to use integrated circuits. Not only in the R&D labs of semiconductor manufacturers, but in the universities, like here at the Solid State Electronics Laboratory of Stanford University in Palo Alto. The facilities you see here in this integrated circuits lab are made available by funds from many industrial organizations. Our lab at Stanford is a miniature of the production facilities you've seen in industry. It was built with the help of contributions from the majority of our nation's semiconductor manufacturers. Right now, we're working in several areas. We do basic research in integrated circuit technology. We're doing circuit research using the unique capabilities of integrated circuits. We also develop devices which incorporate ICs. And we conduct research in several peripheral areas. As an example of our research in IC technology, we're studying new ways for getting impurities into semiconductors. Normally, this is done by diffusion. We do the same thing by ion implantation. This machine takes individual ions and accelerates them, ramming them into semiconductor material much the same as you would shoot a bullet into a bale of hay. Right now, this is a much more expensive process than diffusion, but it's a different technique. Here, we're not interested so much in developing the technique as we are in learning the fundamentals. How heavily can you dope materials, and what kinds of materials can you dope this way? Let's look at an example in the field of medical electronics. Here, we're using IC technology to develop an array of fine probes which a neurologist can implant down in a living brain to study the potential at different points on a single neuron. Here, you're looking at one of the masks prepared by the student doing this research. We're developing probes using the same technology as for the metallization patterns on ICs. The probes will probably be of gold. This would have been impossible before IC technology. One of the most dramatic devices being developed is this reading aid for the blind. This is a reading device in which ordinary printed material is converted to a tactile image, which is presented by a closely spaced array of 48 piezoelectric reeds. By resting his finger on the vibrating reeds, the blind person can sense a vibrating and grainy facsimile of the material being viewed. The great advantage is that this machine enables a blind person to read the printed page. This version is relatively large, even though it incorporates integrated circuits. Ultimately, one 70 by 90 mil chip will take care of all the necessary electronics to drive one vibrating reed.
Certainly, integrated circuits are used in many present-day applications, but we mustn't forget one very important factor, and that is the reliability of an integrated circuit. It is a reliable device. In the industry, we've logged almost 80 million element hours without a failure. That's reliability.
We have considered many different things regarding integrated circuits. One question which we might ask is, why do people care about integrated circuits? Well, there are many reasons. Certainly one of them is the reliability factor that we were just considering. The second one is the fact that they are inexpensive. Even today, it is often less expensive to do a function with integrated circuits than it is with separate discrete components. The fact that they are small is important. This board here contains many functions, many more functions than we could get in this volume otherwise. Finally, there are new functions which can be achieved with integrated circuits that just plain couldn't be achieved any other way. Harry, we've considered a large variety of topics on this program. I'm wondering if you'd be willing to summarize it for us.
Yes, let's summarize. We started out by telling you what an integrated circuit is. This is an integrated circuit. It's a piece of silicon into which have been built all of the necessary components to perform an electronic function. The piece of silicon in a blow-up picture looks like this. All of the functions are there. We've taken you through the design and building of an integrated circuit, from a circuit diagram through masking to wafer processing, and finally on to the final packaging of an integrated circuit. We've showed you that it takes a lot
Of extensive testing.
to prove out an integrated circuit. And finally, you've seen a lot of the uses, both present day and future uses, for integrated circuits. Hopefully, we've given you some ideas on how you can put integrated circuits to work for you.
So there we have it, Fairchild Electronics with their summary of the development of the integrated circuit, preceded by numerous early documentary films on the development of the transistor by Bardeen, Brattain and Shockley, working at Bell Telephone Labs in the late 1940s. This is VK3 Alpha Mike Lima, and in a few moments we'll open up on 147.475 for callback, and hopefully afterwards we probably will do a bit of zoom on the computer on my right. The only trouble is we've had a webcam failure tonight. I think that webcam on the Zoom machine is not working, so with many thanks to Mick, VK3AML, I've put his camera, the one you're looking at me in, to work tonight. So we're on the standby equipment. All this panic occurred a little bit before we went to air and activated the live stream, so it threw me a bit. Otherwise I would have prepared introductory remarks a lot more carefully than I was able to. But this all happens within 10 minutes of going to air. You get thrown into a tiz. So, without any further ado, let's go over to 147.475 and see who's about for a callback. VK3 Alpha Mike Lima now calling CQ and standing by for any calls.
VK3 Alpha Charlie Zulu.
VK3ACZ so far. Peter, nice to hear you there. The subject matter this week I thought was a little bit on the dry side, but I couldn't very well do weeks on the history of valve technology and broadcasting and all the rest without including the transistor. But with a lot of this stuff, particularly the development thereof, you get into fairly heavy semiconductor chemistry and nuclear physics, so sometimes the average person is left a little bit high and dry by the explanations, particularly when you have 3 Nobel Prize winners trying to describe to your average Joe how they worked out how to produce P and N-type germanium in the 1940s. VK3ACZ, with a pause for any other breakers, VK3AML.
VK3AML, I nearly said in the group, VK3ACZ returning. Good evening, Chris. Good evening, listeners. Dry? Oh, heavens no. Absolutely loved it. 1968 Bell Labs, the production line, those very attractive YLs there. The picture quality was absolutely superb, given the fact that I'm only looking on a mobile phone size screen anyway, not having a computer screen to look at it at. I wondered how ICs and transistors were made today, leave alone 50 years ago, so riveting stuff. The only problem at this end was that I kept getting buffering, and I'm sure it wasn't at your end. My internet connections proved to be very unreliable. This afternoon I went back to 3G for a while. I don't know what was happening with Profitcom, but the internet's not been happy all day at this location. But anyway, something jumped out at me. You must have caught the bit where Mr. Shockley said, "Oh, we might even get flat TV screens one day." Nah, that'll never happen. But anyway, fantastic broadcast. I don't know who would call that dry, but we wish I'd seen all of it. I had to give up the video picture, the image, about 10 or 12 minutes before the end of the broadcast because of the problem at this end. Anyway, hopefully none of your viewers had that. And missed you last week, was up at Shepparton. Just quickly, I'll say it was a great ham fest to go to. Really impressed with the number of people who showed up. Bought a nice book on propagation, a few little odds and ends. But it was certainly interesting, again, putting faces to voices and all that sort of stuff. I went out to visit Radio Australia and was pleased to see that it all looks pretty much all there. The only problem I had is that I was intending to work the DX, but I couldn't figure out where to plug in my PL259 hi-hi. Anyway, back to you, Chris. Hopefully Dave turns up. Oh, I did listen to your broadcast from last week. Only this morning I got to listen to the whole lot, and I was pleased to see that Dave turned up in the comments section at least. That's why I thought he might be here tonight. But anyway, he might have gone back to England to see why Her Majesty died or something. Oh boy, hasn't that been a bit of overkill? But we won't go there. In terms of media coverage, VK3AML, VK3ACZ.
VK3ACZ and no group, VK3AML. I'm glad to hear you got up to Shepparton. I wasn't able to get up there because of commitments with Prue, who news this week is not good, I'm afraid, Peter. She's had a scan because she wasn't making the progress with the spinal surgery that we thought she would. And it looks like there's part of the spinal cage that they installed that's worked itself loose. So it looks like she has to go under the knife again. She also has a hip replacement to be done. So it's going to be probably another year out of our lives while the recovery for this goes on. Consequently, I'm going to be in the ham shack a lot, or down at the street doing most of the shopping and bussing about for the family. Not that I begrudge that at all, but it's just a damnable shame for Prue, having been locked down with COVID for 2 years now, to have what appears to be coming up for another 2 years worth of lockdown with physical infirmity. Getting older has knobs on it, I must say. Look, I won't dwell on that. The Hamfest, how was it? I'd be very interested in a greater description of the sort of stuff you saw up there. Obviously, you went out to Radio Australia for a look. I believe there's one antenna system still standing out of the 5 or 6 they originally had, pointed at different parts of the world, and I think the remaining antenna is pointed at Europe. But whether it's actually workable, because there were a number of very big switches involved with it, is another question entirely. I believe the local radio club up there are looking, the Shepparton Radio Club, who held that Hamfest, are looking at installing some sort of historical display at the remaining building, because the building has been declared sacrosanct, given a heritage listing. But that occupies only a very small part of that site, which is otherwise going to be developed as residential housing, as I understand. VK3ACZ with a pause for any other breakers. VK3AML.
Still nothing at this end. VK3AML, VK3ACZ. Well, first of all, the most important thing, that's awful news about Prue. I'm very sorry to hear that, and boy, is that going to make a big dent in daily life for some time to come. I'd be encouraged, though. The hip replacement seems to be one of the least of the worries. I could not believe my next-door neighbour a few years ago when she was home from hospital 4 days after a hip replacement. When I was nursing in the 70s, it automatically meant 3 months in hospital because they didn't even try to get you ambulant for a few weeks. And some of the older ones in poorer condition just didn't make it. They saw the parallel bars and the physio and gave up and passed away. The others encouraged you and inspired you with their determination to get back on the figurative horse that had bolted them. But yeah, none of that problem now. You can be back home within 4 days of the hip replacement. Not that it's to be looked forward to either. And I'm sorry about the other operation that's required. Oh boy. More time in the shack. Well, it might be the universe's way, Chris, of telling you it's time to get that SDR radio that you've been desiring for so long. Okay, Radio Australia. Well, what I could see, when I used to spend overnighters up there back when I was, before I was retired, I would go out to have a look at Radio Australia, and I tried to cast a mental picture in my mind of what was still there. I see the orange brick building still there. There were 3 main clumps of antennas, which is actually more than I remember from all those years ago. But I was also regaled on the Saturday night with a couple of the Shepparton Radio Club members boasting about how wonderful it was when they worked the DX. One group were on 160 metres for most of the night and worked every VK. Another group were on 40 metres working the US, constantly getting 30 over 9 reports back from the US stations. I did my very best, as you could probably imagine, to get myself in the good book so that I might be considered for the next time they go to play radio at the site, and apparently it's likely to happen again. I hope so. I'm just gratified to see there's so much there, and I've never understood it. I keep hearing the phrase curtain array, but when you look at that huge spider web of wires crisscrossing and going back and forward in every possible direction, it ain't the symbol rhombic that I would envisage. However, very effective, because I had a wonderful time in Hawaii, sitting on the balcony of my hotel room looking out over the ocean with my little receiver listening to Radio Australia, and I felt quite at home. And as you could probably imagine, I wouldn't feel like that if I was listening via an internet connection through the telephone lines, but that's a psychological thing. I think that's what I can say about Radio Australia. The Hamfest, just a lot of people, some VK2s and all that came across the border to call in. I was quite surprised at how... Oh, yes, a couple of things about you. First of all, the coverage of the Mount Wombat repeater, 2-metre repeater, is really startling. I was so surprised. Some VK2s get into it quite easily. I also heard your name mentioned too. One of the Shepparton guys said that he's heard you on the repeater, so you know about that. But coming back in the car, I drove through Seymour, Yea, and I was still listening to a conversation as I was starting to go down the hill towards Melbourne, down Mount Slide, or whatever it's called, near... well, I was a long way past Glenburn, and I was still getting it, so yeah, very impressed with that coverage. Lots of people, mainly seniors. Oh, I had a very pleasant chat with VK3AML, because Tom was up there all enthusiastic. He's produced his own little YouTube video of it. A bit distracting with the noise, the background musical accompaniment that he's got with it, but it probably doesn't give you a real idea of how many people there were. It was pretty well patronised. Can't tell you about particular stuff. I think there was a lot of the usual thing. The only thing that really jumps out at me is that 2 kilowatt linear amplifier for $7,995. But anyway, enough waffle from me for this over. Back to you, VK3AML, VK3ACZ.
Have we got any other breakers on the frequency? VK3 Alpha Mike Lima standing by.
VK3 Bravo Lima X-ray.
VK3 Bravo, I think it's BLX. G'day there. Would you like to take it for an over? VK3 BLX. Graham, is it? VK3AML.
VK3AML, Ellen Group, VK3 BLX. Handle is John. And good to hear you on again tonight, Chris and Peter, I think it is there. Did miss the first part of your broadcast tonight, probably the first 20 minutes or more, but I did catch the rest of it, and I must say it was very interesting stuff. Not a bit dry at all, Chris, not a bit dry. Sort of brought back lots of memories. I sort of started working with the PMG as it was back in about 1972 or something like that, maybe 71, and they were doing a lot of work with TTL logic, which is sort of what I cut my teeth on. I remember there was a bit of DTL stuff kicking around, so it was all pretty early stuff. And when you look at the complexity of the what would you call it, the layouts, if you like, the photo templates for the integrated circuits of the time, well, I guess they were probably around about late 60s or 70. And you compare now to what they must look like for something like the CPU in an iPhone or something like that. My goodness, haven't we come a long way? I did see some time ago when I was sort of hunting around on YouTube a very interesting two-part film in fairly ordinary quality, sort of like VHS quality if it was that. Looking at the development of semiconductors in Japan primarily, certainly the first part of it was, after the Second World War, when they started trying to emulate what they knew was going on in the States. It's really fascinating because the facilities they had were just very, very modest compared to what the Americans had at their disposal, and the Japanese were trying to grow, I think, germanium at the time in sufficient purity to, to get some decent semiconductors that they could actually do some development with. And everything was quite rudimentary, sort of real Heath Robinson stuff, manually controlling the temperatures of things with probably a variac or something. It looked, really tricky, but they actually managed to get some decent results and made some progress. The rest of the program was from the American side, I think, and their movement into the manufacturing phase of transistor development, much of it very similar to what was in your material there tonight. But one thing that they did spend a lot more time on in that footage, if you can find it, it's worth a look, was the difficulties they had with reliability. The footage you had tonight there didn't really mention any of that. It made it all seem like it was fairly plain sailing and they got all this stuff to market and it's all very reliable, but it wasn't anywhere near that good. In fact, they had some pretty awful failures where they got stuff into production, got it out to customers, got it into equipment, and it started failing due to packaging, due to probably ion migration and things like that in the chips. So there were some interesting tales about the downsides of all the development. But anyway, I found that all rather fascinating, I'd have to say, and it just really does point out how far we've come, doesn't it? VK3AML in the group, VK3BLX.
VK3BLX and group VK3AML. Yeah, interesting. Just bringing my level down there a bit. I'm over-modulating a bit on the stream. There are all sorts of problems with the early ICs. I know that they, with the linear ICs, particularly for hi-fi preamp use, the quality of them was suspect. They were designed for hi-fi standards, and then they found unexpected couplings between components, and one of them was investigated in a thesis that was done by an old friend of mine, Rod Reynolds, VK3AAR. I think Rod's still on deck. He's not very active with ham radio. He used to be very active on 160 metres in the 70s. And Rod did investigations of linear ICs, which I think PMG or Telecom Australia were using back in the 70s, and found that these ICs would give you very low distortion above 1 kilohertz. But as you got lower and lower in frequency, the resistors on the surface of the chips were so small that they could actually drift in temperature up and down with the cycles of the audio, which in turn would affect parameters like the beta of nearby transistors, causing a sort of a distortion at low frequencies that they hadn't struck before, a distortion caused by thermal coupling, because the thermal inertia of components that small was very small. Normally, if you'd made a circuit that way out of discrete components, would have had no problems, because of course there'd be very little communication of the thermal modulation from one component to another. But on a chip with microns between the components, this was a new problem with crosstalk, I suppose you'd call it, of a thermal type across the chip surface. And Rod did as I understand, a thesis on it. Might have been in his MSc thesis, I'm not sure. But certainly that was the case back about, I think he did that back about 1976, a long time ago. Rod AAR was one of the contributors to Bill Orr's radio handbook of venerated memory, sort of up there with the ARRL handbooks. I don't think Bill Orr is still alive anymore, but his radio handbook, if you can get a hold of them from the late 70s and 80s, they're a real gem of a source for all information on RF and ham radio design. I think I might have seen the two-part film. Terry, VK3FTJS, has made the comment that quite a few of the films I put up tonight, the repetition rate looked very strange. I have to explain, Terry, that these videos are uploaded to various industrial sites at a variety of frame rates and a variety of codings. And when you try to connect them together in a stream, where you have something videoed at 30 frames a second and being converted to 25 frames a second, frequently there are effectively video beats, video jerks between one standard and another, and there's bugger all you can do about it unless you have some very high-end professional equipment, which I don't. I just have the home-based PC video editing gear, and not a huge amount of time to spend on it. Back to what you said, Peter, and I'll hand it round to you in a moment. The curtain arrays at Shepparton, I didn't know exactly how they worked either, until one day I was at Dave VK3ASE's in Ormond, in the place where he's recently moved from, and the previous programming director of Radio Australia, Nigel Holmes, was there. Nigel, who I now think is VK3DZ. And Nigel said, look, I can show you a diagram of all of this from a very old book. And he pulls off Dave's shelf a copy of the RMIT handbook for broadcast ops from about 1960 or something. And there is a diagram of all of the antennas at Shepparton, and in spite of the fact that they look like a spider web, they're actually fairly simple dipoles and reflectors, all stacked horizontally and vertically, and pointing in different directions. That's somebody I really should get on video and run an interview for an evening. Nigel Holmes, VK3DZ. Be warned, Nigel, I'm after you. To talk about all of that. But rhombics haven't really been the go since the 1950s. They were great if you've got lots of real estate, but apparently for their size, not hugely effective in gain. It's better that you use these curtain arrays. But if you want more information, I suppose VK3DZ, if you can get him on the air, Nigel Holmes. The Mount Wombat repeater I get from here. I can get into it on this transceiver and the vertical I've got outside quite adequately. It's on the verge of my range, I must admit. It's only about strength 4 most of the time, but I do get it all the time, irrespective of conditions. And I think it's up at about, it's close to 1,000 metres up, I think, 3,000 feet in the Wombat Ranges. Wombat Ranges? No. It's the range south of the Hume Highway, whose name I've just forgotten. You'll probably know. But it's excellently placed to cover the whole of northeast Victoria, basically, and into New South Wales. And I frequently have chats with it because it's one of the few repeaters apart from Mount Maston that gets me north of the Great Divide. VK3ACZ and the group, back to you for perhaps more on the Shepparton Hamfest, VK3AML.
VK3AML in the group, VK3ACZ. And good evening to you, John, and thank you for coming up to make it so that we can say in the group. And you're about 40 over 9 with me in Bosnia. Baronia. Hi. Well, thank you for your explanation about how the antenna system works, because just looking at it, it didn't make an awful lot of sense. And if you could get him on the air, that would, on your Saturday night broadcast, that'd be even better, Chris. Good stuff indeed. And the other funny thing about it is that I remember when I was up there, I would have a communications receiver with me, and I was a bit worried about blowing the thing up by turning it on when I was too close to it all, having no idea what half a megawatt or whatever they run it might do to a flimsy little transistor radio. But I was amused to find out that the radio, which was normally fairly sensitive, you only needed to be 5 or 8 k's down the road and you could no longer hear Radio Australia. Such must have been the directional nature of it all, and you did say they had reflectors, so that probably makes perfect sense there. Just something else. Because I did say in my last over that somebody there mentioned that you come up on the Mount Wombat repeater, so yeah, I wish I could get it. I certainly don't. I also don't have the luxury of being able to get into Mount Tassie either. I can only do that from the top of the Dandenongs, that 2,000 foot high pile of dirt being in the way for me, but I gather not for you, because I think you've said before you can get into... but then when the Troppo's going, I do get Mount William on 2, 6 and 70. Not all at once usually, but one at a time. Somebody there also said to ask you if you were Charlie from Box Hill. I'm guessing you'll either know or not know what that's about. I won't elaborate any further. And just as a bit of an aside, my news for the week, Chris, is that I went to the toy shop on Monday just to buy a $9 connector and had an IC705 follow me home, the little QRP radio with bandscope and all that sort of stuff. And I had so much fun with it after some basic setting the bandscope up the way I wanted and frequencies in the band stacker. Went out and played portable on Tuesday and had some 5x5, 5x4 type contacts with Europe on the long path, Germany, England and Wales, and had an absolute ball just running 5 watts. It's capable of 10 with an external power supply, but I got ticked off by a Queenslander once for saying that I was QRP when I was admitted to running 6 watts with my little FT818. So I've kept it down at 5 watts and been having an absolute ball with that. And the only other thing of interest is I've had 2 contacts in the last week on 20 metres with Ukraine. Now, whether they're transmitting from Ukraine or not, weren't at liberty to say, and I didn't dare ask. I just tried to be encouraging and said that we send our best wishes to you from Australia for success in your endeavours, and I'm sure they knew what it meant without daring to get political. But again, I hope they're transmitting from home, because I thought it was an awful thing that they weren't allowed to when war first broke out. Anyway, I'm wondering if you know anything about that yourself, because I don't know what the status is with Ukraine hams at all. VK3AML in the group, VK3ACZ.
Okay. have to think very carefully as to how much I say without getting too deep into the politics. That's the first I've ever heard since the outbreak of war of anybody hearing a Ukrainian station, I must say, let alone communicating with them, so congratulations. And it's a bit of a relief to hear that they feel sufficiently at ease to do that. A number of amateurs have taken a very strict line that we should still communicate with Russian hams because what do the Russian hams have to do with the war? Well, my understanding is this. Russia, particularly under Putin, is a totalitarian regime. And if I start talking to Russian hams, my feeling is that it puts the people I'm talking to in Russia in a situation of being seen as a potential security risk. So by me talking to the Russians, I may be endangering the security of them and their family if I say anything wrong, meaning anything political. And knowing the sort of person that I am, having been involved with politics over a very long period, including with radio, I probably would say something wrong. So I make it a rule, only for myself, mind you, I make it a rule that I don't speak to hams in Russia until such time as what is going on in the Ukraine ceases. We are, after all, sending military support equipment to the Ukraine at the moment. So to that extent, Australia is involved. And that being the case with those Bushmaster vehicles particularly, I'm thinking, which they're sending another shipment of, according to the news today, I just feel that it's in the interest of my security and the security and safety of Russian hams for me not to communicate across that divide. Okay, I'll get off the soapbox, and other hams have actually criticised me for mixing that with ham radio, but I just feel very uneasy about that, just as I would have felt uneasy about communicating with German stations after the Austrian Anschluss of 1938 or the invasion of the Sudetenland in the same year, and for very similar reasons. In fact, the reasons are frighteningly similar. Getting back to John VK3BLX, the two-part film, yeah, I think I've come across that film, and I think it's one of the major Japanese manufacturers. It could have been Sony or Sanyo or one of those that was involved with that film, and I might run it. Just as an explanation, if you see technical documentary films of the type that I've been showing the last few weeks, some of them made by government, some of them made by sponsored documentaries by companies like Fairchild or Bell Telephone, frequently if you see a crappy copy reproduced on YouTube in 240p definition and you can trace its title back, you will find that the YouTube clips are actually derived from uploads that have been made from films earlier uploaded to the Internet Archive, which is a resource that very few people seem to use. And on the Internet Archive, the technique is you go into the list of downloadable files, MP4, Matroska video, MKV, and you usually find a quality of upload there that is far in excess of what they've put onto YouTube. So in many cases, if I find clips with extremely poor definition, very bad sound, I can go back to the Internet Archive and get much better results by digging back several generations in upload. I hope that covers it. As for semis in Japan using ad hoc techniques. I've heard stories of the way highly technical equipment is made in China that kind of matches that now. Japan used to have the primitive techniques. Now it's right up there with the major manufacturers of Silicon Valley. But China, there was one person I met who worked in a factory that was producing the Chinese version of one of the expensive dual lens reflex cameras. It could have been Rolleiflex, a Chinese copy. And you would be surprised, their lenses, for example, at the Chinese copy place, they were using glass that was not much better than bottle glass, and rather than using complex computer-controlled lens-making machines, they were using things like treadle lathes with rouge and all the rest of it to make the lenses. But they came up with, for all of that primitive manufacturing, they came up with there's that other computer rebooting again. They came up with really good equipment that was 90% as good as the original article, but at 40% the price. And with that, I'll hand it round to John VK3BLX, VK3 Alpha Mike Lima, who will be booting his second computer.
VK3AML, the group VK3BLX. Well, that's rather fascinating that they could get such good results with such inferior equipment, but I guess if you really put your mind to something, it's amazing what you can do. They must still have been able to coat lenses and all the rest of it to a pretty high standard if they could get, pretty reasonable optical results. It's hard to imagine how they would be able to create, I'm not sure what vintage that was, what era, but assuming that you'd be looking at multi-element lenses and stuff even then, it sounds like quite an achievement considering the simple equipment they were using. Another thing I was going to comment on was one of the steps in the development of the transistor, which was mentioned there, and certainly Fairchild were right in the mix there, coming up with all sorts of, first-line development. The silicon epitaxial transistor was the one that I remember because I think I was still a schoolboy when they started advertising those, and I managed somehow to, I think with the help of my father, who took me down to the Fairchild office in Toorak or somewhere or other, and I secured a few samples of these new, Fairchild silicon epitaxial transistors, and they were dirt cheap compared to the other stuff that was around at the time that, I'd been paying lots of dollars for. Might have been pounds, in fact, pre-1966, and these things were much cheaper, and I was fiddling around on VHF, probably with Super Regen receivers and God knows what else, and these things were like magic. They just worked so well, and they were so much cheaper than the other things. I can hardly believe it. So I remember those little black domes with their little gold legs very clearly, and of course they really took over for a while. I don't exactly know why Fairchild disappeared. Do you have any idea, Chris, what was behind their eventual demise? I guess they were taken over, but why they were taken over and didn't take somebody else over, I really don't know. Not much else to add other than that, but it's quite interesting looking back, isn't it, at all those early years. And the other thing too is the quality of the actual documentaries, the way they're put together, all very matter of fact, all very clear, all very concise. I thought if it was made today, it'd probably have to be all terribly entertaining and woo-ha and all the rest of it. Not nearly as effective as the old ones were. Good stuff. VK3AML in the group, VK3BLX.
VK3BLX and the group VK3AML. It's interesting the changes that have occurred with documentaries since the demise of film as regards video, because the sort of people that were involved with film and the sort of preliminary setting up that they would do for each shot because of the cost of the medium, which was very high in the case of hard copy film. You would only employ professionals to control the cameras for that medium, and you would make sure that you got the shot spot on first take. These days with video, you can just leave the camera running forever and hope that somewhere in 3 hours of shooting 20 seconds will be usable. So there's a different character of producer out there. The other thing is that unfortunately in the old days, particularly when organisations like the Post Office, Shell Oil, who else? There were a number of film units associated with larger major manufacturers and commercial organisations, ICI. The Post Office one's the one that sticks in my mind because they did quite a few documentaries in the 40s, 50s, 60s and 70s on telecommunications. And in 1981, was that the year, I think? I was employed by an organisation as a researcher for an organisation called McMahon Video and Films to research. Was it McMahon, I think? No, it wasn't. It was Film Australia in Lindfield in Sydney employed me to do the footage research and historical research for a film called Ringing True, which was made for the centenary of the first Australian telephone exchange. It was 1980, because the first Australian telephone exchange, Will Street, was 1880. And I got down to Melbourne doing my research, and I needed some footage from the Post Office film unit. And the first thing the Post Office guys did, I forget where the building was, but they grabbed me and sat me down, and I was grilled as to why Film Australia, the Commonwealth Film Unit, effectively the Commonwealth government organisation, was encroaching on their field because they felt that their jobs were threatened. And in fact, quite a few of those government department film units, CSIRO still goes as a video unit, but it had a film unit too. And there was quite a bit of tension between the various organisations producing films at that time. Nowadays, they produce videos almost on a shoestring, as I do. But the quality is questionable. By the way, look at my nose. I'm just looking at it in the monitor. It's bright red. That means I haven't switched the heater on. If it gets cold, my nose is an extremely good temperature gauge. Oh, dear. But yeah, it's the old-style documentaries tended to be educational, short, to the point, and were intended for intensive training of whoever it was that they were aimed at. Now, Fairchild existed, as I understand it, until about 1982 or 83. They were the leading IC maker, along with Texas Instruments and one or two others in the 70s. But I think the organisation was split up into component parts because it dropped behind in sales in about 1982, and the various parts were subsumed into other organisations, as I think Stromberg Carlson, which was mentioned there, and Burroughs, I think, also disappeared about that time. So they don't. These corporations tend to be fairly fragile in situations where takeovers can occur. Anything else to comment on? Ion migration in chips. Yeah, I believe that metal migration in very early point contact transistors, which were available early to mid 50s when they were incredibly expensive. The problem with point contact transistors, apart from the extremely poor maximum collector current you could get out of the things, was the fact that the point contact was so small that even the voltage applied to it would cause metal migration of the point, which would induce the beta of the transistor to slowly rise over time, and eventually, particularly in IF strips, the IF would take off, it would oscillate, it would have so much internal feedback that it had become unstable. The transistors got better with time and unfortunately got too good. VK3, thank goodness we don't have them anymore. VK3ACZ and the group, VK3AML.
Yeah, VK3AML, VK3ACZ in the group returning. And going back to your earlier comments about Russian hams, I just feel uncomfortable. I don't really know where I sit on it, so I just avoid it. And you hear a few on. Interesting, they weren't allowed to contest in one of the recent contests that were happening on air, but again, I just don't know. The Ukraine stations that I did work well, not much more than exchange signal reports, do have on their QRZ page with address withheld. I'm aware that some time ago, that according to the Wireless Institute broadcast, they were allowed to broadcast from inside Ukraine so long as the transmissions came from remote outside of the country. I don't think that's still the case, because I'm pretty sure one of them said, well, actually, no, it might not be. He said he was in Kiev. But anyway, that's enough of that. As I said, I just feel uncomfortable, and that's enough for me to wait until it's all over. If it was anything, if it was a democratic country, it'd be a different story. I might be inclined to say more than I'm entitled. William Bradford Shockley, you motivated me. I mean, I've done it before, but I didn't remember. You motivated me to look up a little bit about him, and I see that he passed on to the next life in August 1989. That's not all that long ago, so he got to see a lot of the benefits of the invention. And I know it's not all up to him, but remarkable in terms of how prolific he was with academic achievement and prowess and all that sort of stuff. Certainly the Crapopedia paints a pretty unflattering sort of image of him. That's only one source and one possibly biased representation of him, but all the same, very interesting, and I owe you a debt of thanks as usual for encouraging me to look up all that stuff. One last thing, so you're not Charlie from Box Hill? Because somebody at the Shep Hamfest thought you might be, because of the similarity to the voice to somebody who now comes up on the repeater. VK3AML, VK3ACZ.
Well, indeed I was. I'm just trying to think. I first came up on CB radio with a friend of mine's handheld 100 milliwatt 27.24 meg handheld in 1967, 55 years ago, and we just called each other by our Christian names. I called him Roland on the air, he called me Chris. But later on, at times during the 80s particularly, I was thrown CB radios by various people casting them off. And I'm just trying to think of the name of the rig. Uniden President Grant, I think, or something like that. And everybody had a moniker that they used, and I was living in Surrey Hills, but I was about no more than 100 metres from the borderline with Box Hill, and I didn't want people visiting me having heard the appalling behaviour and language that used to go on 27 megs. These days, the 27 meg people tend to be only the hardline DXs from the old days, so they're a bit more serious. But in those days, in the 80s and early 90s, it really was starting to go to the pack in the literal sense. So I called myself not Chris but Charlie, and not Surrey Hills but Box Hill. And I stuck with that for quite a while, and people knew me as Charlie, and I thought, well, you know, Charlie, there are lots of proper Charlies on there, so I became another one of them. But over time, we actually had people... There's a certain mentality that goes with parts of CB radio that really is rather unfortunate, particularly if you're an adult trying to talk to adults in every sense of the word, and that is that certain people on CB seem to make it a sport to make the maximum nuisance of themselves and to try to start arguments. And I wouldn't often be lured into that. I tried to keep a gentlemanly approach, but ultimately it was impossible to do, and I gave up on it. But in the interim, we had a break-in at one stage where I knew all of the techniques necessary for minimum loss on coaxial cables and getting maximum gain out of antennas and getting the maximum height and all the rest of it. And I was in an excellent location for 27 megs because we were right on top of the highest hill in Surrey Hills, elevation 120 metres, about 2 streets away from the massive telecom tower at the corner of Harding Street. And what happens is, with some of these CBers, their thinking is so phallic that if you have a bigger antenna than theirs or a bigger signal than theirs, somehow their manhood gets threatened. And the result is that you get things like your fence being sprayed, coax being cut, and only because you've got a decent signal and try to operate properly. So eventually I just gave up on it. I thought, this has got knobs on it. And I gave up on it at about, I haven't used Charlie Box Hill since about 1996. It's that far back. Did you have any experience with CB, John, VK3BLX? And I suspect we all have at some stage. VK3, Bravo Lima X-ray, VK3AML.
VK3AML in the group, VK3BLX. Let's just put that down. No, I had never had any experience on CB. I'd have to confess. I came from sort of the schoolboy hobbyist who got a shortwave radio, used the family shortwave radio to tune into hams and was immediately hooked. And I regarded the CB lot as the strangest lot of reprobates that the world had ever created. So I wanted nothing to do with that lot. Little did I realise that would be a very important seeding ground for ham radio operators in times to come. So yes, it's funny that. But nevertheless, I couldn't say that I didn't do a bit of piracy on my own, but not on 27 meg. It was on the ham bands using a concocted call sign, just once or twice, just to prove that what I'd built would work. And those were the days. Nothing much to add, so I'll put it back to you, Chris. VK3AML in the group, VK3BLX.
Yeah, I saw a posting on the text that Mick 3ADD is laughing his head off because he was one of the people that knew me as Charlie Box Hill years ago. Many years ago, when he was in his late teens and I would have been in my late 20s, I think. Gosh. And he comments, CB is full of little men. I suspect if the threat to their phallic property is so great that they're little in more ways than one, Mick. Compromised in the wedding tackle department. Particularly the way they go on when they hear somebody with a decent signal. Oh, you must be running a 1,000-watt linear. No, mate, I'm running a 3-element beam. Don't you realise that gives me more gain in dB than 1,000 watts through a vertical? And they just don't get it. Anyway, as you say, Mick, CB's full of little men. It's a pity because I've met some of the nicest people on CB, but they've had to battle through such a bloody, shoulder deep with verbal excrement to get a decent conversation. I've not struck that sort of thing on ham radio. I have struck people who can be nasty on ham radio, but in a very different way. There are professional jealousies, and if you don't like what they like, automatically you're a bad person. The one particular chap, I remember having him attacking me because I had the temerity to say that FT8 and WSJT was of no interest to me. It's not that it's bad. I'm not criticising it. It's just no interest to me. But, some people take things the wrong way. VK3ACZ, I'm sure you know what I'm talking about. VK3 Alpha Mike Lima.
VK3AML and the group VK3ACZ, of course. And I noticed with the Sunday morning EMDRC broadcast after the Wireless Institute broadcast, somebody, if he comes up on that, gets a very nasty serve and has called names to do with harming children. So yes, there's some nasty people out there. And I've heard a particular person that the allegation is true, and also that it's not. So I'm keeping right away from that one. Being able to pass complicated exams and prove you know a little bit about technical theory and all that doesn't mean that you've got the morality or the smarts or the courtesies to go with it. And my experience with 11 metres is more of a listener than anything. I note that in the early 70s it was like the amateur bands, because I'm sure that everybody was afraid that they would get raided by the RIs if they swore and carried on and did that sort of stuff. At least that's the impression I got. I know that not long before it became legal, everything went quiet because the RIs had been doing a lot of raiding in the area that I used to live, so that quietened things down a lot. When I next turned on to have a listen, there was a huge, constant carrier of AM signals and horrible, nasty heterodynes and all that, and you couldn't listen to a thing, and it was all primary school stuff. It was all very lowbrow, get a headache and put aspirin in your boots sort of stuff. And it still is today if I bother to listen. One thing that surprises me about it is that you've got people bragging that they're using a 7610. Another fella's saying he's just switched on his 1 kW linear, and there's obviously no restriction placed on it. But honestly, I don't hear conversations that don't include a lot of expletives, and I get the feeling that they can't make each other understood unless they can't be understood by each other unless they're using that kind of language, and it's not very highbrow stuff. That might be different to my experience there. My listening experience might be different to what you just said a few moments ago, Chris, but that's been my take on it. I couldn't, for the life of me, ever be on 27 megs. It's just, well, for example, not so long ago there was some sporadic E coming down from Sydney, and the sum total of the content there was the Melbourne people were telling the Sydney people if they ever come down here they'd get their heads punched in and to pass on quietly back to stay in your home city, and that was the size of it. Most of us, I think, most hams would be happy to work a VK2 on 10 metres with sporadic E, but not threaten them if they ever left their sunny state that they'd get their heads punched in. But anyway, that's the size of it, and enough picking on the on that particular band. I'm happy where I am, thank you. So anyway, the rumour was true. The funny thing was the person up in Shepparton who told me about Charlie from Box Hill wouldn't have even been born when you were operating, so I didn't bother to find out how he knew, but you weren't spoken about in derogatory terms. It just got mentioned that they thought that you were Charlie from Box Hill. So anyway, mystery solved. Get on with the next subject. VK3AML, VK3ACZ.
Yeah, well, CB had its funny side too. I mean, there was, I think I've told you this story, but it probably bears repeating because there'll be a different audience for it this time, hopefully. You could always tell on 27 megs when the short skip was in, because there was, in the early 90s, there was a lunatic asylum in Beechworth. And they must have... I find this very funny, but anyway, at the time it was annoying. They must have had a psychiatrist on staff who was convincing people in locked wards at Beechworth Psych Hospital that if they had trouble communicating with people, a good way to learn how to communicate was to get on CB radio and chat there. Well... the result in terms of psychiatric fallout on 27 megs was astounding. I can only call it that. There was one guy there who would... he'd come on the air and he'd say something like, well, who's going to have an argument with me today? To which somebody would reply, what do you want? You know, excrement head, using the... term. And then this nutcase in Beechworth would start. You get motor-mouth abuse non-stop for the next 2.5 hours. He had 2.5 hour overs. And I think he only stopped either when his finals were on the verge of burning out or when he literally raved himself hoarse. It was a phenomenal performance, and I only wish I had a tape recorder running at the time. Oh God, it was awful. And that was on an AM frequency. I think these guys didn't get very much money together to buy their rigs, and usually it was on the call channel on 27 megs, which I think was channel 11. So whenever the short skip was in, there'd be this raving nut job on the channel blocking everybody else from calling with this massive AM signal. I believe he only had 5 or 10 watts, but he certainly must have had a big antenna at Beechworth. And the other place where you'd know that the short skip was in was Tasmania, because usually when the skip came in on 27 megs, the signal would only come down when it reached northern New South Wales, Ballina, Coffs Harbour, up to about Toowoomba. If you got double hop, you might get Rockhampton, less often. But very rarely did you get the short skip from Sydney, and even more rarely still, fortunately, from Beechworth. VK3BLX and the group VK3AML.
VK3AML and the group VK3BLX. Well, I must say your descriptions there of life on the CB band hasn't made me wish I'd experienced it. No, something I'm quite happy that I didn't get involved in. I'm a bit short on comments tonight, boys. I'm tinkering away at something here on the bench here, so I might just carry on with that for a few more minutes. If anything pops into my empty skull, I'll come up again, but just at the moment, nothing to add. VK3AML, the group VK3BLX.
Yeah, it's getting a bit late to fire up Zoom too, so my apologies to Rolly if he stayed up for it, but I'm going to have to do a bit more work. Either the Zoom camera that I've got has ceased to function, or something's gone wrong with the system that I'll have to get stuck into the software and try to work out. Whichever way it goes, it's unlikely I'll be able to get Zoom working tonight. So apologies to those interstate who'd like to come back to us via Zoom. I'll certainly get it going next week. But under those circumstances, probably we should wind it up soon, Peter. I've had a horrendous night here technically. I mean, the system just simply failed to operate about a quarter of an hour before I went to air. And I had to completely reset all the parameters within the OBS streaming software that I've got, and reset all of the controls for the standby camera that 3ADD very kindly made available to me. Terry 3FTJS has just put in the comment, being a nut job is a standard requirement for CB and UHF CB. I wouldn't say 27 megs anymore, Terry. 27 megs is really are the sort of hardline DXer types seem to have survived there. But UHF CB, I agree, has completely gone to the pack. During the day, you're crowded off the air by commercial users, crane operators, you name it, and at night the drunks and drug takers, and but it's very different once you go more than 100 kilometres out of Melbourne into the bush. CB radio is totally different. Tends to be used by farmers. I remember there was one repeater I could get through from Surrey Hills on UHF, and that was the Mount Terrible repeater in the Upper Goulburn Valley near the 10 Mile and that place up the Upper Goulburn where 3FVJS was the 10 Mile, Jamison, south of Jamison, Woods Point. All that area was served by this Mount Terrible repeater. I could get through it, and the people on that were very strict on usage, very understandably, because it was used to communicate up and down the valley before the days when they had satellite phones. It was your only means of communicating from one place to another up and down the valley if you didn't want to use the phone network or weren't on it. So in the bush, CB radio is a whole different ball game and very much more useful and very much more friendly. And I get the impression, because the smaller number of users out there per unit area, everybody knows everybody, and if you step out of line, you'd be stomped on pretty quickly by your contemporaries on the air. So round to Peter 3ACZ for a final. I will have to cut it short, fellas. And hello to Van Dan Escobar, and my second computer has automatically debooted itself for some strange reason. It's a day full of gremlins at VK3AML. And thank you for being there, Van Dan Escobar. Jamison, yeah, but there's a name of a town between Jamison and Woods Point, and I just can't remember the name of it. Anyway, it'll come to me. So round to you, Peter, with a pause for any final breakers. VK3ACZ, VK3AML.
VK3AML in the diminishing and disappearing group, VK3ACZ. Yeah, you're listening to a different 27 megs than I've listened to, Chris. For a little while there, I thought, what better way to tell me when 10 metres is open? But no, that doesn't cut it anymore, especially when we've got our Wireless Institute or whoever beacons around 10 metres, plus the IBP 10-metre beacons worthwhile. It's much more interesting to know what's happening outside of Australia as well. I'm listening to the IBP beacons a fair bit lately, but no, I don't hear anything of a wholesome family listening sort of happening on 27 megs at all. It's real lowbrow fare, is my experience. Again, yours must vary. You must be hearing different stations to me. You certainly haven't heard Darren in South Croydon or No, I better not. I better not go any further than that. Some high-class operators indeed. But anyway, yeah, it's been another enjoyable broadcast tonight. Always appreciate your effort in what you produce for us, for our entertainment and for our edification and expanding our knowledge base and all that. Some wonderful images of people again who are no longer with us, and again highlight for me was forgive me for having a one-track mind, but did like looking at those gorgeous young YLs there on the production lines there and doing that intricate work with the magnifying glasses and that sort of thing as well. But anyway, until next week, Chris, if not before, have a great week and best wishes for you and especially for Prue, and hope all goes well there. VK3 AML, VK3ACZ. Good night, Chris, and thank you.
Okay, Peter. Do we have any stations finally before we close? VK3AML, standing by.
Yeah, I'll second Peter's remarks there, Chris. Thank you for going to all the trouble of producing that show and every other Saturday night show. They're always well worth our time, and I can't imagine how much time you spend, but it's much appreciated. VK3AML on the group, VK3BLX was clear.
And good night to you, John.
Yeah, good night, fellas. And good night to Rolly in Auckland if you're still watching. I hope you get a better night's sleep after all these. Next week I'm planning on doing a compilation of different films of prominent names in electronics and physics. Thomas Edison made quite a few very early sound films, newsreel items, which I'll run. Lord Rutherford of Nelson, Lord Rutherford, who was the chap who came up with the idea of the magnetic detector, later involved with nuclear physics. The Braggs, William Bragg and Lawrence Henry Bragg, the only father and son team to be jointly given a Nobel Prize for physics. I think it was 1913, and it was for crystallography, but William Bragg had done a lot of work in wireless telegraphy in Adelaide when he was at Adelaide University in the 1890s, and his son Lawrence was an excellent lecturer on aspects of physics, electromagnetic waves and electricity and superconductivity, which the Royal Institution had the foresight to record as a couple of lectures in 1965, which I hope to run next week with enhanced sound. Quite often when these things were recorded with an optical soundtrack, today they sound pretty woofy and full of hum, so they need a bit of work, and I'll certainly give them that before they go to air. But next week, famous names in physics. And with that, I'll leave you to it on 147.475. This is VK3AML. Thank you for the patience of people who might want to use this frequency for other things. We only use it once a week, and we hope to see you next week, not at 9:30 p.m. I'm intending to start half an hour earlier next week at 9 p.m. on Saturday night, to take account of people like poor old Rolly, who watches in from Auckland 2 hours ahead of us and basically has to stay up till 2 o'clock in the morning if he wants to see the end of this live. So we'll start a half an hour earlier, and hopefully we'll finish half an hour earlier, which means midnight local time. Other bit of news, just before I close, is that VK3AML, my old compatriot on modulated light communications, Mike Groth, is coming over to stay with us for a couple of days in a couple of weeks' time, and I'm hoping to get him either live on the air on one of our Saturday sessions, or pre-recorded if we can't manage to get him at the time when he's visiting. So it'll be an interesting couple of weeks coming up, and as a result of the interest tonight, I will hammer Nigel Holmes for an interview. This is VK3AML, now closing on 147.475. Wishing everybody all the best till 9 p.m. next Saturday night. And now it only devolves on me to close on the stream. I'll just turn down the inputs from 2 metres. I want to particularly thank Mick VK3ADD for the spare webcam. If I hadn't had this thing tonight, I wouldn't have been able to go to air at all. I don't know why the other webcam just refused to come on. So I had to do a complete software reset and plug in the spare webcam that I would have used for Zoom. Otherwise, I would have tried a Zoom contact earlier. But under the circumstances with that webcam becoming iffy, I didn't think it was worthwhile taking the risk. So with that, I'll say cheers until next Saturday. Thank you for being on the stream, those of you who are beyond the reach of our VHF. VK3BA, thank you very much for being there. Mick, ADD, VK3ZGC, thank you for being there. Terry 3F2JS, thank you. Rolly ZL1BQD. Who else have we got there? Tom George, I think he's up in Canberra. Just thank you for watching, Tom. And to all those who are who will be watching on the replay, cheers to you. Please do, if you are watching from interstate or overseas and can manage to be up and about at our 9 p.m. starting time, we will open Zoom, give you an opportunity to come back to us if you can't come back to us via radio, but that'll be next week. So with that, all the best until then. VK3AML now going clear of the live stream. Have a good evening. Oh, and Ardran, hi and bye.